Hello everyone. So in this pre-lecture tutorial we're going to wrap up chapter 15 on chemical equilibrium by discussing Le Chatelier's principle. And so the basic idea behind Le Chatelier's principle is just to be able to predict how an equilibrium system will react to changes or disturbances in the equilibrium state of that same system. And normally these changes can occur in very specific ways. So, for example, one way in which we can have a disturbance to an equilibrium system is to change one of the concentrations of the reaction participants. So either remove product or increase the amount of product, or remove reactant or increase the amount of reactant. And so basically what Le Chatelier's principle says regarding changes in concentration is that the reaction will work to counteract the change in concentration. Now, what that means is if I remove product, then the equilibrium process will proceed towards the product side of the reaction to replace that product that I removed. Or if I add additional product, then the equilibrium process will actually proceed in reverse away from the products towards the reactants to consume that additional product that I actually have included in the equilibrium system. If I change pressure, all right, and this is more applicable to gas phase equilibrium. The equilibrium system will actually move towards the side of the reaction that will cause the pressure to go back to the original state of the equilibrium system. So essentially, if I have a change in pressure with a gas phase equilibrium process, then basically the reaction shifts towards the side of the equilibrium that opposes the change in pressure. Okay, if I have a change in temperature, all right, so here, if we're going to assess the change in temperature, then we're going to have some idea of the heat of reaction. Okay, and if I change the temperature of the equilibrium system, then basically the equilibrium system will shift in such a way to utilize the heat of reaction to return to the initial state. So again, the equilibrium reaction will shift towards the side of the reaction in which the heat of reaction counteracts the temperature change. And lastly, if we consider the presence of catalysts, remember catalysts, what they do is they increase reaction rate. And if you recall, one of the first things that I warned you about related to equilibrium is that equilibrium and kinetics are not the same thing. And so if we include the presence of a catalyst in an equilibrium system, what that does is that will not alter the equilibrium concentrations of the equilibrium system, all the catalyst will do is it will affect the speed at which I actually achieve equilibrium. So again, the speed at which equilibrium is reached is affected, but the actual equilibrium concentrations are not going to be affected. So I sort of wanted to provide you with sort of a summary or a set of guidelines to use to apply to equilibrium processes, though in all fairness, it's probably not going to be as clear unless we do a couple of examples. So let's do a couple of examples within this tutorial, and then it'll give you a basis on which to actually attempt the follow-up assignment for yourself. So let's take this first example here that's labeled number 3. And within this example, basically I have carbon dioxide and hydrogen gas forming carbon monoxide and water vapor. Now note that I also have heat listed on the reactant side of the equation. And so what that indicates is that this reaction requires an investment of heat. And so that means this is an endothermic reaction. And so in this first question, if we're being asked, is heat absorbed or released by the forward reaction? Again, if the heat is listed on the reactant side, that means it's a requirement, which means heat needs to be absorbed by the forward reaction in order to get the reaction to go. Now, here in part B, this is where we're going to be applying those postulates of Le Chatelier's principle that I provided to you in the previous slide. So here, they're saying which direction will the equilibrium shift if carbon monoxide is added? Well, carbon monoxide is here on the product side. And so according to Le Chatelier's principle, basically the reaction is going to work to counteract whatever change in concentration that I provoked. And so if I increase the concentration of carbon monoxide, the reaction is going to fight to actually decrease the amount of carbon monoxide again. And so the only way that can happen is if the reaction proceeds backwards towards the reactants, or it proceeds to the left. So here, the equilibrium will shift towards the left. Now, in the next prompt, we're told, well, what about if I add carbon dioxide? Well, if I add carbon dioxide, then again, remember the equilibrium process is going to fight to undo whatever change I provoked. And if I increase the carbon dioxide, then that means the reaction should proceed forward to decrease the amount of carbon dioxide again. And so that should cause a shift towards the right. Then they're asking, well, what happens if I remove hydrogen? So now I'm going to get rid of hydrogen. So if I decrease the hydrogen, that means that the equilibrium process will want to put some hydrogen back again. The only way that's going to happen is if the reaction proceeds backwards to actually produce more hydrogen to counteract the fact that I removed some. And so that means this reaction should proceed to the left to produce more hydrogen. The next thing that they asked is, well, what happens if I add a catalyst? Well, if you recall, we just said that a catalyst is not going to alter your equilibrium concentrations. It's just going to get you to equilibrium faster. And so here, basically, there should be no change. What about if the temperature is increased? Well, if the temperature is increased, that's going to deal with this heat term that I just circled here in pink. And so, again, according to Le Chatelier's principle, then the reaction is going to shift towards the side of the reaction in which the heat of reaction counteracts the temperature change. So if I increase the temperature, that means I'm making the reaction system hotter. Well, if the heat is on the reactant side, then that means that the equilibrium system is going to try and shift the equilibrium away from where there is heat present within the process. Since the heat is present on the reactant side, and if I increase the temperature, that means the equilibrium process should want to shift away from the heat and towards the products. So that would cause a shift to the right, towards the products. If I cool the system, then basically the reverse should happen. If I cool the system, then that means that the equilibrium process will want to shift backwards towards the heat to drive the temperature back up again since I'm cooling the system. So in this particular case, the equilibrium should shift left towards the reactant side of the equation. And lastly, they're asking, well, what happens when the pressure is increased? And so if we check our postulates of Le Chatelier's principle, the reaction is going to shift towards the side of the equilibrium that opposes the change in pressure. And that actually involves the number of moles of gas. And the way that that works, if the pressure is increased, then the equilibrium system will want to shift towards the side with fewer moles of gas. Because remember, if I have fewer moles of gas, that means fewer gas particles. If I have fewer gas particles, then that means fewer collisions, and the fewer collisions there are, then the less pressure there will be. And so whenever I'm dealing with pressure changes, I want to count up my number of moles on either side of the equation. And if I'm going to increase the pressure, that means that the equilibrium process should shift towards the side of the equilibrium reaction equation in which I have fewer moles of gas. Now, in this particular case, I have 2 moles of gas on the reactant side, and I have 2 moles of gas on the product side. Since the number of moles are equivalent on either side, then basically there would be no effective pressure on this equilibrium system. And so that would mean I have no change in this particular reaction system if I increase the pressure. Now, here in this particular example that I've included underneath, example number 3, that's not the case anymore. Because if you notice, I have 3 moles of gas on the reactant side, but I have 2 moles of gas on the product side. In this case, I'm decreasing the pressure. And so again, if I'm decreasing the pressure, the equilibrium system will want to build that pressure back up again. And so in order to do that, it's going to shift towards the side with more moles of gas. Because again, the more moles of gas I have, the more particles there are. The more particles, the more collisions, and the more collisions, the more gas pressure. And so if I decrease the pressure, the reaction should want to go towards the side where I have greater numbers of moles of gas particles. So for this particular reaction equation, that's an equilibrium in example 4, then a pressure decrease should cause me to shift left in this case, because there are more moles of gas on the left-hand side of this equilibrium equation. So based on the examples I've given you, go ahead and try the follow-up assignment. Obviously, we'll be discussing this in class in greater detail and reviewing over the next couple of days as well. If you have any questions, by all means email, or if not, then ask in class. Have a good night.